Let us design a column of size 300 mm by 400 mm with unsupported length of 7 meter. The effective length ratio is 0.85 in both directions. The column is subjected to factored axial load of 1500 kN. The factored moment at top end of the column about major axis is 60 kN and about minor axis 40 kN. Assume column is bent in double curvature in both directions and the moments at the bottom end is equal to 50% of corresponding moments at top. The grade of concrete and steel are M30 and Fe415 respectively. The effective cover to the reinforcement is 60 mm. So let us start the solution. First, calculate the moment at the bottom end of the column. These moments are equal to 50% of the corresponding moments at the top. Therefore, the bottom end moment about the major axis is equal to 30 kN, while that about the minor axis is 20 kN. Next, let us determine whether the given column is short or slender. According to IS 456-2000, a column member is considered short when both the slenderness ratio LEX by D and LEY by B are less than 12. Using the given effective length ratio of 0.85 in both directions, we find that the effective length about the major and minor axis is equal to 5.95 meter. Now, calculating LEX by D, we get 14.88 and for LEY by B, it is 19.83. Since both slenderness ratio exceeds 12, this column is classified as long or a slender. In the next step, we will compute the eccentricities. According to clause 25.4, all columns must be designed for a minimum eccentricity. This minimum eccentricity is calculated as the unsupported length of the column divided by 500 plus the lateral dimensions divided by 30, subjected to a minimum value of 20 mm. So let us calculate the minimum eccentricity denoted as EX mean and EY mean corresponding to the major and minor axis respectively. After putting all the values and solving, we find that EX mean equal to 27.33 mm and EY mean equal to 24 mm. Since both minimum eccentricity values exceed 20 mm, we can compute the moment due to minimum eccentricities by multiplying them with the axial load. Solving further, we obtain moments due to minimum eccentricity about the x-axis and y-axis as 41 kN and 36 kN respectively. According to the IS code, for a braced column without any transverse load along its heights, the total design moment is the sum of the initial moment and the additional moment. The initial moment is calculated as the sum of 0.4 times mu1 and 0.6 times mu2. Here, mu1 represents the smaller end moment, which is assumed to be negative if the column is bent in double curvature, while mu2 on the other hand corresponds to the larger end moment. Importantly, the initial moment must not be less than 0.4 times mu2. In this example, the column is braced and bent in double curvature. Therefore, mu1 will be negative. Hence, mui can be expressed as 0.6 times mu2 minus 0.4 times mu1. The additional moments will be computed as per the expressions given in clause 39.7.1. Let us proceed with the computation of initial moments. In this example, the moments at the top end are larger than those at the bottom ends. Therefore, for the expression of the initial moment about the major axis, mu2x represents the moment about the x-axis at the top end, and mu1x corresponds to the moment about the x-axis at the bottom end. Similarly, for the initial moment about the minor axis, mu2y denotes the moment about the y-axis at the top end, and mu1y represents the moment about the y-axis at the bottom end. After putting all the required values in the expression and solving it, we find that the initial moment about the x-axis, that is muix, is equal to 24 kilonewton meter. This moment should not be less than moment due to minimum eccentricity about x-axis, but here it is less. Hence, the value of initial moment about x-axis should be equal to 41 kilonewton meter. Similarly, we get the value of initial moment about y-axis equal to 16 kilonewton meter. This value is also less than moment due to a minimum eccentricity. Hence, the initial moment about y-axis should be equal to 36 kilonewton meter. In next step, let us compute the additional moments about major axis and minor axis as per the expressions given in the clause 39.7.1. After putting all the required values and solving, we get max equal to 66.42 kilonewton meter and may equal to 88.47 kilonewton meter. According to the clause 39.7.1.1, additional moments calculated using clause 39.7.1 can be multiplied by a factor k. However, since the values of PUZ and PB are unknown at this stage, we assume k equal to 0.5. Let us denote KAX as the factor to multiply with MAX and KAY as the factor to multiply with MAY. After multiplying the additional moments MAX and MAY by these factors, we find that MAX equal to 33.21 kilonewton meter and MAY equals to 44.23 kilonewton meter. Next, let us compute the total design moment by summing the initial and additional moments. As a result, the total design moment about the major axis denoted as MUTX equals to 74.21 kilonewton meter. This value exceeds the larger acting moment of 60 kilonewton meter at the top about the same axis. Similarly, the total design moment about the minor axis denoted as MUTY equals to 80.23 kilonewton meter. Again, this exceeds the larger moment of 40 kilonewton meter at the top about the minor axis. Next, let us design the trial section. As the column is subjected to moment about both major and minor axis, we need to compute the resultant of these two moments. After solving, we get the resultant moment MUR equal to 126.68 kilonewton meter. As the total design moment about minor axis MUTY is greater than that of about major axis, consider the resultant moment acting uniaxially about minor axis. Consequently, this design problem simplifies to the design of a column subjected to axial load and uniaxial moment. So, let us get the parameters required for percentage steel computation from interaction chart. As the resultant moment is acting about minor axis, the depth d in d dash by d is equal to width of the column, that is b. After putting values and solving, we get d dash by d equal to 0.20. Pu by FCK BD is equal to 0.417 and the value of mu by FCK BD square is 0.117. Now select the appropriate interaction chart from SP16 by assuming reinforcement is distributed equally on all four faces of the column and Fy equal to 415 Newton per mm square and d dash by d equal to 0.20. For this, we have chart number 45. The more details about interaction charts and how to use it for the reinforcement calculation, please refer the earlier video of design of a column with uniaxial moment. The link is given in the description. So let us get the value of percentage steel from this chart. For this, in the chart, mark the mu by FCKBD square value 0.117 on the horizontal axis and draw a vertical line from it. Similarly, mark the Pu by FCKBD value 0.417 on the vertical axis and draw a horizontal line. Get the intersection point of these two lines. Here, this point is approximately between the P by FCK curve for 0.12 and 0.14. Hence, we can consider the value of P by FCK at this intersection point equal to 0.13. So, after putting the values of FCK, we get the percentage steel required as 3.9. From this, get the total area of the steel required. After calculation, it is equal to 4680 mm square. Next, let us fix the number of bars to be provided as longitudinal reinforcement. Select the bar diameter as 28 mm. The number of bars required are around 8. Hence, provide 8 number of 28 mm dia bars as longitudinal reinforcement. Thus, the total area of a steel provided at all faces is 4924 mm square. The percentage steel provided is 4.10%. The ratio of percent steel provided to FCK is equal to 0.136. In the previous steps, the provided reinforcement was unknown. Therefore, we couldn't calculate the values of PUZ and PB. As a result, we assumed K equals to 0.5 during the computation of additional moment. Now, in the current step, we know the provided reinforcement area. Therefore, to determine the actual value of the factor K, we must compute the actual values of PUZ and PB based on the provided steel. So, let us obtain the value of PUZ based on the formulation given in clause 39.6. In the expression, AC is the area of a concrete only, and the ASC is the area of a steel provided. After putting all the values and solving, we get PUZ equal to 3086 kilonewton. Next, let us get the value of PB about major and minor axis, that is about X and Y axis. The PB can be computed by using the expression for rectangular section given in table 60 of SP16. Based on this, we can easily write the expression to compute PB about X-axis, that is PBX, and about Y-axis, that is PBY. In this expression, we need values of K1 and K2 about X and Y axis. So, let us compute K1X and K2X based on d dash by d ratio from the table 60 of SP16. For the X axis, we have the d dash by d ratio equal to 0.15. Therefore, the value of K1X is equal to 0.196. Similarly, for the rectangular section with equal reinforcement on four sides, the value of K2X is 0.203. Next, compute K1y and K2y based on d dash by d ratio for y-axis from the same table 60 of SP16. The d dash by d ratio for y-axis is 0.20. Therefore, the value of K1y is equal to 0.184. Similarly, the value of K2y is 0.028. After putting all the values in the expression of Pbx and Pby, we get Pbx equal to 805 kN and Pby equal to 676 kN. After getting the values of Puz and Pb, let us compute the value of k about x and y axis, that is Kax and Kay, using the expression in clause 39.7.1.1. After putting the values of Pu, Puz, Pbx and Pby, we get Kax and Kay equal to 0.695 and 0.658 respectively. Now let us recompute the additional moment Max and May with the actual values of factor k as per the expression given in clause 39.7.1. After putting all the required values in the expression and solving it, we get actual Max and May equal to 46.61 and 58.21 kilonewton meter. With the actual values of additional moments Max and May, let us calculate the actual total design moment Mutx about x-axis and Muty about y-axis. After putting the values and solving the expression, we get Mutx equal to 87.19 kilonewton meter and Muty equal to 94.21 kilonewton meter. In next step, check whether the reinforcement provided is sufficient or not for the safety of column under biaxial loading. For this purpose, we can use the expression given in clause 39.6. In this equation, Mux and Muy are the design moments about x and y axis. Mux1 and Muy1 are the maximum uniaxial moment capacity about x and y axis respectively, and alpha n is related to Pu by Puz. So let us compute the maximum uniaxial moment capacity about x-axis, that is Mux1. For the x-axis, d dash by d ratio is 0.15. Hence, we will refer the interaction chart number 45 from the SP16. From this chart, we will calculate the Mux1 based on the value of Pu by FCK BD equal to 0.417 and the ratio of percentage steel provided to FCK equal to 0.136. So let us compute Mux1 from interaction chart. For this, in the chart, mark the Pu by FCK BD value 0.417 on the vertical axis and draw a horizontal line from it. Locate the point P provided by FCK on the above horizontal line. Draw vertical line from that point. Get the value of Mu by FCK BD square at the horizontal axis. Here we get that value equal to 0.135. Now assign Mux by FCK BD square value to Mux1 by FCK BD square. After putting the values of FCK, B and D in this equation, we get Mux1 equal to 194.4 kilonewton meter. This is more than design moment Mutx. Similarly, compute the maximum uniaxial moment capacity about y-axis, that is Muy1. For the y-axis, d dash by d ratio is 0.2. Hence, we will refer the interaction chart number 46 from the SP16. So, to get MUY1 from interaction chart, mark the PU by FCKBD value 0.417 on the vertical axis and draw a horizontal line from it. Locate the point P by FCK on the above horizontal line. Draw vertical line from that point. Get the value of MU by FCKBD square at the horizontal axis, and here we get that value equal to 0.115. Now let us get the value of MUY1. As MUY1 is about y-axis, the value of B is equal to depth D and value of D is equal to width B. After putting the values of FCK, B and D in this equation, we get MUY1 equal to 124.2 kilonewton meter. This is more than design moment MUTY. Next, let us compute alpha n. As per IS code, alpha n is related to PU by PUZ. Hence, calculate PU by PUZ, which is equal to 0.486. As per IS code, for the values of PU by PUZ equal to 0.2 to 0.8, the alpha n vary linearly from 1 to 2. For the values less than 0.2, alpha n is equal to 1. And for values greater than 0.8, alpha n is 2. The values of alpha n with respect to PU by PUZ is given in graphical format in figure 1. Here, PU by PUZ is lying between 0.2 and 0.8. So, compute the alpha n by linear interpolation formula. After solving, we get alpha n equal to 1.477. After getting all the required values to check the column for safety under biaxial loading, substitute in the expression given in clause 39.6. After solving, we get the value equal to 0.97. This is less than 1. Hence, the column section with the provided reinforcement is safe under applied loading. In next step, let us compute the diameter and spacing of the lateral ties. As per IS code, the diameter of the lateral ties shall not less than 1/4 of the diameter of the largest longitudinal bar and in no case less than 6 mm. Here, only 28 mm bar diameter is used for longitudinal steel. Hence, the 1/4 value of dia is 7 mm. Therefore, use the 8 mm diameter of lateral ties. Next, the spacing of the ties shall not be more than the least of the following. First, the least lateral dimension. Second, 16 times the smallest diameter of longitudinal bar. And third, 300 mm. Here, first, least lateral dimension is 300 mm. Second, 16 times smallest die of longitudinal bar is 448 mm. So, provide the spacing of ties equal to least of all three values, that is 300 mm. Hence, provide 8 mm dia ties at 300 mm center to center. Finally, let us summarize the design and the reinforcement detailing. A slender column of size 300 mm by 400 mm subjected to axial load with biaxial moment is designed with M30 grade of concrete and Fe415 steel. 8 number of 20 mm dia bars are provided as longitudinal reinforcement, while 8 mm dia lateral ties are provided at spacing 300 mm center to center. If you like this video, then share your thoughts in comment section, subscribe this channel and press the bell icon to get the notification of such interesting videos for visual and simplified learning of various civil engineering topics.